Hello students. So today I am doing class for class 10. So today we will do theorems related to tangent to a circle. So what is the meaning of tangent to a circle? You draw a circle. So let us draw a circle with the center O. And there is a point P on the circle. And let us take the point P on the circle. Now draw a straight line which touches the circle at the point P on it. So this straight line will be the tangent. So what is the tangent to the circle? The straight line which touches the circle at the point P on it is known as the tangent to the circle. And this point P is known as the point of contact. This point P is known as the point of contact. So P is equal to, this P is known as the point of contact. So what is the point of contact? The point P on the circle at which the tangent touches the circle is known as the point of contact. Is that clear? So if you join this PO or OP will be the radius of the circle through the point of contact P on it. And you should know that this OP is perpendicular to the tangent always. This radius OP is perpendicular to the tangent. Now we will prove this theorem here. You have to prove that the tangent to a circle at any point on it is perpendicular to the radius passing through the point of contact. Your P is the point of contact. So OP is the radius through the point of contact P. You have to prove that this radius OP is perpendicular to the tangent passing through the point of contact P. Okay. Now we will prove this theorem. Okay. So now the theorem is, you have to prove that the tangent to a circle at any point on it is perpendicular to the radius passing through the point of contact. Okay. So let us draw the figure now. Now this is a circle whose center is at the point O, right? And you take any point P on the circle. We are taking any point P on the circle. Now draw a straight line which touches the circle at the point P on it. Okay. Suppose this T. Suppose PT is tangent to the circle. Suppose this PT is tangent to the circle at the point P on it. Right? And then you join O and P. So OP will be the radius of the circle through the point of contact P. So what is given here? Let us write it. Now we will prove it. Now write down the answer. So here given is a circle with the center, a circle with the center O is given. Given a circle with the center O is given, right? The tangent PT is drawn to the circle. The tangent PT is drawn to the circle at the point of contact. At the point of contact, CONTACT, at the point of contact P on it. The tangent PT is drawn to the circle at the point of contact P on it. Okay. Now this O and P are joined. O, P are joined. O, P are joined. So what is OP here? OP is the radius through the point of contact P. So OP is the radius. OP is the radius through the point of contact. OP is the radius through the point of contact P. Okay. So what is given here? A circle with the center O is given. The tangent PT is drawn to the circle at the point of contact P on it. Then O and P are joined here. O comma P are joined. So OP is the radius through the point of contact P. So now what is to be proved? You have to prove that the tangent to a circle at any point on it is perpendicular to the radius passing through the point of contact. That means you have to prove that OP is perpendicular to the tangent TP through the point of contact P. Okay. Now to prove, now what is to be proved? The radius OP is perpendicular to the tangent TP through the point of contact P. The radius OP is perpendicular to the tangent TP through the point of contact P. You have to prove that OP is perpendicular to the tangent TP through the point of contact P. Okay. So now you can copy it. Now in this case you have to do the construction now. So let's do the construction now. Now the construction is, any point Q is taken on the tangent TP other than P, right? So any point Q. So any point Q is taken on the tangent TP other than P. Okay? Then O and Q are joined. Right? Then O and Q are joined. So let us assume that this straight line OQ intersects the circle at the point R. Okay? So now we will write here. So what is the construction here? Any point Q on the tangent TP, any point Q on the tangent TP other than P is taken. Any point Q on the tangent TP other than P is taken. Then join O and Q. O comma Q are joined. O comma Q are joined. Let the line OQ intersect let the line OQ intersect the circle at the point R. Okay, you have understood? So this is the construction part. Now we'll do proof. Now we should prove that OP is perpendicular to the tangent TP through the point of contact P. Now proof. So now in this case, this OR is less than OQ, isn't it? So R is a point on the line OQ. So from the figure we can write down that OR is less than OQ. So from the figure we can write down that OR is less than OQ. But from the figure we can write down that OP is equal to R, OP is equal to R, because these are the radii of the same circle. So radii of the same circle are always equal. So being radii of the same circle, being radii of the same circle. So instead of this OR we can write OP. So therefore OP is less than OQ. So here OP is less than OQ. Now here Q is any point on the tangent TP other than P, isn't it? This Q is any point on the tangent TP or PT other than P. And so in this case, this OP is the least distance. So OP is the least distance of all the line segments that is drawn from the center O to the point Q. And this least distance OP is the perpendicular distance always. Right? So we will write it here. Since Q is any point on the tangent TP other than P, and from here OP is less than OQ means OP is the least of all the line segments that is drawn from the center O, to the point Q, right? So since Q is any point on the tangent TP other than P, okay? So therefore, what can I write? OP is the least of all the line segments that is drawn from the center O, to the point Q. And you know that this least distance will be the perpendicular distance. So we can write down that. Therefore, the least distance OP is the perpendicular distance. The least distance OP is the perpendicular distance. The least distance OP is the perpendicular distance. Hence, we can write down that the radius OP is perpendicular to the tangent TP at the point of contact P. Hence the radius OP is perpendicular to the tangent TP at the point of contact P. So proved. So we have proved the theorem that the radius OP is perpendicular to the tangent TP at the point of contact P. So we have proved the theorem. Okay. So we'll do the next theorem now. So you can copy it. So now we are doing the next theorem, that is theorem related to a tangent to a circle. So this is your next theorem. Okay. So if two tangents are drawn to a circle from a point outside it, so outside the circle there is a point, and from that point you can draw two tangents to the circle. Now in this case you have to prove that the line segments joining the point of contact and the exterior point are equal. So you can draw two tangents to the circle. You have to prove that the line segments joining the point of contact and the exterior points are equal. You have to prove that the length of the tangent, that is the line segment joining the point of contact and the exterior points, are equal, and they obtain equal angles at the center also. So you have to prove it. Okay, so let us draw the figure now. So this is a circle, right? So I told you that while drawing a circle you have to use compass, pencil, ruler. Okay, so this is the center O of the circle, right? And there is an exterior point P here. So this is the exterior point P, which is outside the circle. P is the point outside the circle. And from P you can draw two tangents to the circle, isn't it? So let us draw two tangents to the circle. Suppose this PQ is a tangent to the circle at the point of contact Q on it. Okay? And you can draw another tangent from the exterior point P to the circle. Suppose this is T. T is the point of contact. That is, T is a point on the circle and T is the point of contact here. Okay? So now PQ and PT are drawn two tangents to the circle. This PQ and PT are the two tangents drawn to the circle with the center O. Here Q is one of the point of contact and T is the another point of contact. Okay, so now here given is what is given? The two tangents, the two tangents PQ and PT. The two tangents PQ and PT are drawn to the circle, with the center O. With the center O, right? So in this case we will join O and P. This center and this exterior point P are joined, and then you can join OQ, and then you can join OT. Is that clear? So now here O comma P, then O comma Q and O comma T are joined, right? So this is the given part. The two tangents PQ and PT are drawn to the circle with the center O. Then we have joined OP, we have joined OQ and OT. Is that clear? So now what is to be proved? You have to prove that the two tangents are drawn to the circle from a point outside it. So if the two tangents are drawn to a circle from a point outside it, then you have to prove that the line segment joining the point of contact and the exterior point are equal. So in this case, PQ and PT are drawn tangents to the circle. So here Q is the point of contact and T is the point of contact. You have to prove that the length PQ is equal to length PT. Okay? So number one, you have to prove that PQ is equal to PT. That is, these two tangents are equal. You have to prove that. Okay? And also you have to prove that these two tangents obtain equal angles at the center. This PQ tangent is making angle POQ at the center, and this tangent PT is making angle POT at the center, and you have to prove that these two angles are also equal. That means this PQ and PT obtain equal angles at the center. That means you have to prove number 2, angle POQ is equal to angle POT. You have to prove that these two angles are also equal. That means angle POQ is equal to angle POT. Is that clear now? So now we will prove it. So now in order to prove these two relations, we have to use the previous theorem. Okay? Now let us prove it. Proof. No construction is needed out here. Right? So now what we will do here is, here Q is the point of contact and OQ is the radius and PQ is the point of and PQ is the tangent. In this case, PQ is the tangent to the circle at the point of contact Q from the point P, and OQ is the radius at the point of contact Q. So from the previous theorem, what can you write? OQ is perpendicular to the tangent PQ. Okay, so let us write here, PQ is the tangent, PQ is the tangent to the circle, PQ is a tangent to the circle from the exterior point P, from the exterior point P to the point of contact Q. PQ is the tangent to the circle from the exterior point P to the point of contact Q. PQ is the tangent to the circle from the exterior point P at the point of contact. Let us write here. PQ is the tangent to the circle from the exterior point P at the point of contact Q on the circle. On the circle. Right? And now OQ is the radius. OQ is the radius. OQ is the radius at the point of contact Q. At the point of contact Q. And OQ is the radius at the point of contact Q. So therefore, what can we write? OQ is perpendicular to the tangent PQ. Is that clear? So here you can write, that is angle OQP is equal to 90 degree. Angle OQP is equal to 90 degree. Also, since T is the point of contact here, OT is the radius and PT is the tangent through the point of contact T. So OT is perpendicular to PT here also. Okay. Since OT is the radius, and PT is the tangent, to the circle from the point P at the point of contact T on the circle, right? Since here OT is the radius, OT is what? The radius of the circle, and PT is the tangent to the circle from the point P at the point of contact T on the circle. So therefore, what can we write? OT is perpendicular That is OT is perpendicular to the tangent PT. That means what can you write? Angle OTP is equal to 90 degree. So these are both 90 degree. So from the previous theorem we can write down that both these angles are 90 degree. So I think I've understood it. Okay. So now we have to prove that these two tangents are always equal. That is PQ is equal to PT, and they subtend equal angles at the center. That means these two angles are also equal. You have to prove it. Okay. Now let us prove it now. So in order to prove PQ is equal to PT and angle POQ is equal to angle TOP or POT, we have to prove that these two triangles are congruent. In order to prove that these two triangles are congruent means equal in all respects. Equal in all respects means equal in all angles, equal in all sides. So in order to prove that these two triangles are congruent, you have to give three reasons. Okay? Now we will prove that these two triangles are congruent, right? So right now, in triangles, which two triangles? POQ and POT, right? So we have to give three reasons here. One of the reasons is OQ is equal to OT. That is OQ is equal to OT being radii of same circle, right? Being radii of same circle. That is OQ is equal to OT. Next, this OP straight line is common to both. OP is common to both, right? And the next one is these two angles are equal, that is 90 degree each. We just proved it. So therefore angle OQP is equal to angle OTP, 90 degree each, right? So because of these three reasons, what can you write? That triangle POQ is congruent. This is congruent sign. Is congruent to triangle POT. I already told you that this means congruent sign. Congruent. This is the congruent sign. Congruent means equal in all respects. Okay. That means they are equal in all angles. They are equal in all sides. So we can write here, therefore, we can write down that PQ is equal to PT. That is proved. So PQ is equal to PT. Both the tangents are equal and they subtend equal angles at the center. That is angle POQ is equal to angle POT. That is, they are proved. Okay. So we have proved that the two tangents PQ and PT are equal and they subtend equal angles at the center. That means angle POQ is equal to angle POT. Is that clear to all of you? So you can copy it. Now we'll do the next theorem. So now we are doing the next theorem, that is, if two circles touch each other, then you have to prove that the point of contact will lie on the line segment joining the two centers of the circle. Okay, so if the two circles touch each other, the two circles will touch each other at a point that is known as the point of contact, and you have to prove that that point of contact will lie on the line segment joining the two centers of the circle. So is that clear to all of you? If the two circles touch each other, then they will touch each other at a point that is known as the point of contact. You have to prove that that point of contact will lie on the line segment joining the centers of the two circles. Is that clear to all of you? So touch each other. It is not mentioned that they touch each other externally or internally. It is not mentioned that. So we will draw both the figures. Suppose the circle touch each other externally as well as internally, right? So let us draw the two figures. Suppose this is the first circle, right? This is your first circle. You have to use ruler, compass, pencil, okay? And also there is a circle here, second circle. Suppose this is the second circle. So in this case, both the circles are touching each other at a point. Suppose that point is, suppose this is the point of contact. Both the circles will touch each other at a point. That, suppose that point is, suppose this point is P. This point P is known as the point of contact. Okay? Suppose this is the center of the first circle A. Suppose B is the center of the second circle. So they are touching each other externally. So यो दुईटा A र B जुन चाहिँ सेन्टर भएको सर्कल छ त्यो सर्कलले बाहिरपट्टि टच गर्दैछ. दुईटा सर्कलले बाहिरपट्टि नै टच गर्दैछ. That means both the circles with the centers A and B touching each other at the point P externally. Okay? So let us draw the figure here also, touching each other internally. Suppose this is the first circle. Suppose this is the first circle whose center is A, and there is another circle here. There is another circle here. There is a small circle touching each other internally at the point P. Both the circles, suppose this is the first circle whose center is A, that is a bigger circle, and for this smaller circle, suppose the center is B. A is the center of the bigger circle and B is the center of the smaller circle. Okay? And both the circles are touching each other at the point P internally. यो दुईटै सर्कलले भित्रबाट टच गर्दैछ नि त P पोइन्टमा. बुझ्नु भएन? That means they are touching each other internally at the point P. So now we have to prove that in both the cases this P is the point of contact. You have to prove that this point of contact P lies on the straight line joining the centers of the two circles. Is that clear? So let us join A and P. And let us join B and P. So here also let us join A, B and P here. You have to prove that P lies on the line segment joining the centers of the two circles. That means you have to prove these A, P, B are collinear. Collinear means lying on the same straight line. Suppose you will say P, Q and R are collinear. C-O-L-L-I-N-E-A-R. Collinear means lying on the same straight line. P, Q, R are collinear. Collinear means all these points P, Q and R lie on the same straight line. So if they lie on the same straight line, then the 3 points are said to be collinear. Is that clear? So now here, so what is given here? So let us write down given the two circles with the centers A and B touch each other at the point of contact. Touch each other at the point of contact P. At the point of contact P, right? So this is given. The two circles with the centers A and B touch each other at the point of contact P. Okay? Now, to prove, what is to be proved? A, P and B are collinear. collinear. C-O-L-L-I-N-E-A-R, collinear. That means all these 3 points lie on the same straight line. That means the point of contact lies on the straight line joining the centers of the two circles. That means AP and B are collinear. Is that clear to all of you? So now construction. Now we have to do the construction here, right? So let us join A comma P and B comma P are joined, right? So in this case, A comma P are joined and B comma P are also joined. In this case also A comma P are joined and B comma P are joined. Now we have to draw a common tangent here. So what do you mean by common tangent to the circle? That tangent which is same for both these circles with the centers A and B is known as the common tangent. So let us draw a common tangent at the point P. Suppose ST is the common tangent. So ST is the common tangent to both the circles at the point of contact P. Okay? And also here also, in the second figure also, you can draw the common tangent ST at the point of contact P. That means this tangent is common to both the circles with the centers A and B. Is that clear to all of you? So now we will prove that this A comma P and B are collinear. Okay? So let us do proof now. Now proof. So now look at the blackboard. Since this P is the point of contact, right? P is known as the point of contact. Okay. So AP is the radius. AP is the radius of the circle with the center A. And since P is the point of contact here, and ST is the tangent at the point of contact P. So from the previous theorem, what can you write? AP is perpendicular to the tangent ST. Similarly, BP is the radius. BP is the radius of the circle with the center B, and P is the point of contact here, and also ST is the tangent at the point of contact P. So here also BP is perpendicular to the tangent ST. Similarly here also you can say, right? So proof is AP is the radius of the circle. You can write AP is the radius of the circle with the center A, with the center A, with the center A, and ST is the tangent, and ST is the tangent to the circle at the point of contact P, at the point of contact P, at the point of contact P on the circle, at the point of contact P on the circle. Okay, so we have written here AP is the radius of the circle with the center A, and ST is the tangent to the circle at the point of contact P on the circle. That means what can you write? AP is perpendicular to the tangent ST. AP is perpendicular to the tangent ST. So AP is perpendicular to the tangent ST. Now similarly, what is BP here? BP is the radius of the circle with the center B, and ST is the tangent, and ST is the tangent to the circle at the point of contact P on the circle. At the point of contact P on the circle. So what can you write here? BP is perpendicular to the tangent ST, right? So similarly you can write down that BP is the radius of the circle BP is the radius of the circle with the center B and ST. What is ST here? ST is the tangent to the circle at the point of contact P. At the point of contact P on the circle. At the point of contact P on the circle. That means what can you write? So therefore BP is perpendicular to the tangent ST. Okay, so here this BP is perpendicular to the tangent ST. BP is perpendicular to the tangent ST at the point P. At the point P. Here also you can write AP is perpendicular to the tangent ST at the point P. At the point P. Okay. Now both the straight line AP and BP are perpendicular to the same tangent ST. If AP and BP are perpendicular to the same straight line ST, that means what can you write? AP and BP lie on the same straight line. Okay? So write down, since AP and BP are both perpendiculars to the same straight line. AP and BP are both perpendiculars to the same straight line ST at the point P. At the point P. So therefore what can I write? AP and BP lie on the same straight line, isn't it? Both the straight lines AP and BP are both perpendiculars to the same straight line ST at the point P. That means AP and BP lie on the same straight line. So therefore AP and BP lie on the same straight line. Lie on the same straight line. That is what can you write? Hence the 3 points. Hence the 3 points A, P and B are collinear. Hence the 3 points A, P and B are collinear. That is, since AP and BP lie on the same straight line. So what can you write? The 3 points A, P and B are also collinear. That means they lie on the same straight line. Collinear means the 3 points A, P and B are collinear means A, P and B lie on the same straight line. So we have proved the theorem. Okay. So you can copy it. So this much is for today. So you can revise all the theorems that we did so far. So in the next class we'll do construction. Okay. So for the construction we need ruler, compass and pencil. Okay. So in the next class we'll do constructions.